Organosilanes are an incredibly important class of compound. They're used in lubricants, many other applications. The problem with them is, though, that they don't really naturally occur, and to make them, we've got to use huge industrial processes that are very energy intensive and use some really quite nasty chemicals. And so some of my colleagues here in the Manchester Institute of Biotechnology have come up with an alternative way of making these organosiloxanes by using enzymes, and this opens the door to cleaner chemical synthesis that might be more sustainable.
Our research is very interested in this class of compounds called the organosiloxanes. These are organic molecules which have, as part of their structure, a silicon-oxygen bond. One can divide up the types of compounds which contain silicon-oxygen bonds into two main areas. The first one is in polysiloxane polymers, more commonly known as the silicone polymers. So silicones are bulk industrial products that have an absolutely vast variety of applications. Important, but perhaps not so familiar to the public, is the fact that they are used as components in the synthesis of more complex organic molecules, so for example pharmaceuticals, agrochemicals. Its production is currently not particularly ecologically friendly. It's rather energy intensive, and if we can find routes to make it more eco-friendly, I think that would be highly desirable. Currently, silicone polymers are not biodegradable. These compounds are now everywhere, including in the polar regions, right? These are completely synthetic molecules, so if they're there, it's probably because we've put them there. So in the longer term, I think it would also be quite interesting to see if we can use our enzymes to help in the degradation and ultimately, hopefully, the recycling of these siloxane materials. About 20 years ago now, some marine biologists in California who were studying this species of marine sponge realized that these sponges used silicon in their skeletons.
Silicatine is an enzyme that is within these sponges, and it takes silicic acid from the seawater and it condenses it within its cells and forms this exoskeleton out of the seawater. And it's this glass exoskeleton made from what seems to be nothing with this tiny little enzyme. And the fact that we can take this and harness it is amazing. You wouldn't necessarily think, oh yeah, that seawater should definitely become a drug.
If we use this enzyme, which is from an organism which uses silicon anyway, perhaps this would be a better starting point to investigate, again, the sort of biological formation of these silicon-oxygen bonds.
This is a colorimetric assay. What that means is that when the reaction happens, a colour is generated, and that's how we can tell how good it is. The deeper the colour, the more successful the assay has been. When you put a protecting group on the alcohol, a silicon protecting group specifically, the compound is colourless. But when you break this bond, it forms the anion, and that is a bright yellow colour. You can use this to measure how efficient the enzyme is at doing its job, because what silicatine does is it makes and breaks silicon-oxygen bonds. So you're measuring how well it breaks this silicon-oxygen bond. And the better it breaks the bond, the more intense the yellow colour is.
What we would like to do is study the mechanism of this enzyme, because it performs a rather unusual reaction in nature, to understand how it performs this reaction from a biochemical perspective, and related to that is to understand the structure of this enzyme. And then going on after that is then how you can then apply this enzyme to performing these sort of chemical synthetic reactions.